we could
okay.
get back on our schedule.
Oh,
Okay.
thank you so much.
You're welcome.
Peter is
Annie, so we're now going into the final session, I think. So we have one invited talk by Peter Stuckey, 2 regular talks by Bob Kowalski and Daniel Hines, and then a final panel on why, since logic languages are so good, why isn't the whole world using them? This is the perennial question, okay? So let me first introduce Peter Stuckey. So Peter Stuckey is one of the major figures in the area of constraint programming, modeling, solving combinatorial problems. So if you're anything in that area, you will know him. So he is professor in Monash University. So I think he's actually probably the one that's the farthest away from the others in Australia, right? And time zone issues. But he has many awards, ACM Distinguished Scientist, Google Australia Eureka Prize for Innovation in Computer Science, University of Melbourne Woodward Award, Fellow of AAAI. So, and he's going to talk about historical and modern things in constraint programming, from CLPR to MiniZinc, there and back again. So, Peter, I give the floor to you.
All right, thank you. Let me bring up my keynote.
So that's Australia behind you?
That's Australia behind me. No, that's a fake background, I'm afraid. It's a Star Wars picture, actually. So I apologize for the thing. I'm having my laptop look at me because occasionally my laptop camera disconnects from the big screen, and then my microphone turns off and all kinds of things happen. But so you're going to have to look at this weird view of me, but hopefully you can see the screen perfectly.
We see 2 slides right now. The current and
see 2. Ah, see you see both. Okay. How can I do this? Ah, there we go. Let's do it without using full screen then. So I don't want to enter full screen. Goodness me. Well, okay, the other option is I close this. And let's try again. Okay, how about now? Is it better?
we see a slide, but a whole bunch of tools around it. But
yes.
could be okay. Yeah.
Yeah, I'm trying to figure out how to get rid of that Zoom window on top of me. All right, I guess okay.
Oh, and we don't see you anymore.
Oh, well, I think you live without my pretty face. I've still got that toolbar. I don't know quite how to get rid of that. There's some way of removing this thing.
If you click on format, it should go away, right? If you click on it again.
Click on this?
On the format thing on the top, right? If you click on that once more, it should go away. Make the slide bigger, maybe.
This thing? No.
No, the thing on the top right called format with the paintbrush in it.
Yeah, yeah. Oh, okay. But it's more that I can go to full screen. I'm just trying to get rid of this. That's interesting. That doesn't happen normally, but we'll have to go with that. How about that? That's not too bad.
It's okay.
Okay. So, yes, so I'm going to talk about from CLPR to MiniZinc. So this is kind of a historical journey, if you want. Of course, all the hard work I'm going to talk about here was done by Guido Tack, Graham Gage, and Yip Decker. And I'm going to talk about basically an evolution of MiniZinc, where we see that where I started off in my programming language sort of research career seems to be where I'm ending up. So just to take you back, so constraint logic programming sort of came from 3 simultaneous advances around 1986 and 1987. So Alain Commerau built Prolog 3, which included arithmetic constraints. So it's a logic programming, the first basically logic programming system that included some arithmetic constraints as well as the usual term constraints. And Pascal van Henterink built CHIP, which was a finite domain constraint addition to logic programming languages. And Jocelyn Jaffa and Jean-Louis Lassalle defined the semantics for logic programming extended with constraints. And this really sort of defined constraint logic programming. And
Peter, I think we see just your slide, the first slide. We don't see you moving slides.
You don't see me moving slides. Fantastic. Okay, what the hell is going on? I'm sharing the wrong screen maybe. Let me stop sharing.
Yeah, probably. Yeah.
Okay, share screen. Where is?
You have to share the right.
Yes, I have to share the right keynote. So maybe that's what was not happening. Okay, let's try again. Now, can you see a separate slide now?
Yeah, this looks very good.
Great.
Okay, sorry. Okay, so that's what I just talked about, the sort of advent of constraint logic programming. Did the slide just change?
Yes.
Okay, good. So for my part, I was one of the people who built CLPR, and this was basically one of the first 3 CLP languages. And here we were interested in incremental linear arithmetic and term solving. So we added incremental linear arithmetic solving. We also had some restricted nonlinear solving implemented by delay. And we did some work also in a powerful sort of simplification and projection of constraints. And this was used for very interesting things like generative architecture and options trading analysis and various things around the world. And just to give you an idea about what CLPR was like, here's the most used CLPR program. You can see it's not very big, it's the last 2 lines of the slide. And this is a mortgage simulator. So what it's writing down is the relationship between a mortgage where you have a fixed repayment. So we have this principal, that's the amount you borrow, the number of time periods in the loan, the repayment amount that you pay every repayment amount, the interest rate that applies at each time period, and then the balance you owe at the end of the loan. And you can see that we can write this down as in a very declarative fashion by saying, well, if I have a mortgage for 0 time periods, then the amount that I owe at the end of the loan is the amount that I owed at the beginning of the loan because nothing happened. It was 0 time periods. But if I have a mortgage for more than 1 time period, well, what happens? It's really that I take my existing amount that I owe, I add the interest, so I multiply by 1 plus the interest rate, I subtract our repayment, and then that's the new amount that I owe to the bank. And there's 1 less time period, and that's it. So this very succinct and beautiful program is really useful because you can ask lots of kinds of questions using it. So what can you do with it? So you can ask a very simple question and you could write a C program to do the same thing. This is basically just simulating the mortgage. So if I say, if I borrow $1,000 for 10 years at 10%, repaying $150 per year, how much do I owe at the end? Okay, I owe $203, a little bit more. But I can ask other questions, right? Because this is the relational programming where there's no fixed notion of inputs and outputs. I can say, well, how much can I borrow if I'm repaying $150 to owe nothing at the end? Okay, so I can borrow $921 if I want to owe nothing at the end of my 10-year period. But you can ask even more sophisticated questions because of our simplification and projection ideas that were available in this system. So I can say, what's the relationship between the principal, the repayment, and the balance for a loan which lasts for 10 years at 10%? And actually, there's a linear relationship between those. The principal is 0.385 times the balance plus 6 times the repayment. And that makes use of simplification and projection. And why was it most used? Because it's a very, very useful tool when you're trying to figure out what to do with your mortgage. Right. So CLP was a very powerful paradigm and it produced state-of-the-art solutions to many, many problems, and particularly CHIP with its finite domain constraints was used in lots of industrial things. And Eclipse Prolog arrived, which had more finite domain and interval constraints. And in fact, we see that all modern logic programming languages include constraint programming features, right? So basically, one of the great powers of the kind of relational view of the world is that that's a very natural way to think about constraints. And constraints are very powerful. Underlying solvers can do a lot. But then I'll say that the fall of CLP, in some sense, was that we came along, well, Pascal van Henterink came along with an alternate approach to tackling the kinds of questions that we're interested in with CLP, which are typically discrete optimization problems. he developed a modeling language for iLog for finite domain constraints. And the big jump was this was a modeling language rather than a programming language. So what's a modeling language do? It basically only allows you to state a set of constraints of the problem. And then you let the underlying solver solve the problem. So OPL did have programmable search. So one of the powers of CLP or LP languages in particular is that we can program the search as part of the program. But unlike LP or CLP languages, it didn't have any meta-programming capabilities. And it turns out that once we start looking at very complicated optimization problems, actually we tend to use those meta-programming capabilities. So we sort of took a step back, but one thing we got rid of was recursion, and that's one of the things that which seems to make programming in declarative languages hard for people. They're used to iteration, but not recursion. All right, so a brief sidestep. So we worked on languages which were kind of in between OPL and CLP. So we didn't quite want to give up CLP. So we worked on the G12 project where we developed Zinc, a solver independent modeling language. So this is designed to, rather than have a fixed solver underneath, have different solvers underneath. But it was a modeling language like OPL. And it was implemented by rewriting using cadmium, and then finally we had Mercury, which is an existing logic programming language for solver implementation below. And sort of this is a new approach to constraint programming, sort of like OPL, but not quite giving up all of the logic programming or full programming language features we're used to. So I only really introduced this because this gave us the Zinc language, and I'll talk just briefly about how MiniZinc arose. So there was a 2006 conference workshop at the Constraint Programming Conference talking about the future of constraint programming. And lots of people were complaining about a lack of standard for CP. So basically, if you wanted to solve a problem using a CP solver, you had to write it for that particular CP solver. And that seemed very difficult. It also made it very hard to compare different CP solvers. And so everyone was complaining. So we looked at this and we thought, well, actually we can take Zinc that we developed, a quite complicated high-level programming language. We can cut it down to be a small thing which should be fairly easy to for every solver to support. And that's where MiniZinc arose. And so we submitted a paper to the CPRR conference in 2007 called MiniZinc, a standard modeling for CP, as our kind of answer to this question, and it was rejected. And then we submitted a slightly different paper by changing the title. Shows you how important it is to get the title right on your papers, to MiniZinc towards a standard modeling language for CP where it was accepted. I mean, there were some other differences, like we actually had a system and some experiments in the second version of the paper, but it was an interesting thing in where you should go with your titles. Be very careful with your titles. So just to show you MiniZinc briefly, here's the mortgage example redone in MiniZinc. So here we've got a parameter t, which is the time period. So just before where we had them as arguments to the mortgage predicate, now they're just given as parameters. The other one, so the t has to be given. So since MiniZinc doesn't have recursion, we can't have an unbounded recursion. So we need to know how many time periods we're talking about up front. But all the rest of the arguments can be variables. Here they're float variables within a bounded range. And then we build up an array of all the mortgage values. That's basically the principal that you owe at every point in the mortgage, and basically build up the same system of equations that we talked about. And so we can answer, like the first question is just, we give it the time, the principal, the interest rate, and the repayment, and it'll print out the balance as 203, like we saw before. The second query, again, here we're just giving a different set of inputs. So we're giving the balance rather than the principal, and it'll print out the result there too. But it can't do some questions that the other one does. It certainly can't do the third question, which relied us to understand the relationship. That requires projection capabilities that solvers don't support. And it can't do other things like saying, okay, if I can repay this amount, how many years do I need to repay to pay off my mortgage? Because here you have to fix the time. All right, that's not a very usual example of MiniZinc, because MiniZinc is really designed for combinatorial optimization, discrete optimization problems. So here's a more realistic example of a MiniZinc model. So this is job shop scheduling. This is a very classical discrete optimization problem. We've got a number of machines and a number of jobs. So each job includes one task for each of the machines. And basically, so we have to assign this in the data here. The M's tells me for each job, for each task within the job, which machine should it run on and how long does it run. And then the decisions we need to make is, oh, I'm missing a var, array job task of var 0 to max duration S. That's the decisions we're going to make as to when do we start each job. And then we write down some constraints. So basically, the first constraint says that every job has to finish before the make span. That's the end of the entire process. The next one says that the jobs, for the tasks in a single job, they have to happen in order. So the teeth job of the teeth task of job J has to finish, so its start time plus its duration has to be before the start time of the next job. And finally, the complex part is that every machine can only do one thing at once. And here we make use of the fact that we have, in constraint programming, we have global constraints like disjunctive, which is basically saying, here's a set of start times and durations for tasks. You have to make sure that none of them overlap in time. And so here we go through each machine, we collect all the jobs, all the tasks for the jobs which run on that machine and collect up their start times and durations and add this global constraint. And then we try to minimize the make span, so to try to do everything as fast as possible. So that's a more typical example of a MiniZinc model. But don't worry if you didn't understand it too much. It's just trying to sort of show you the kind of style of the language. And so actually, how does MiniZinc work? Well, we take data in a model and something I haven't really shown here, a library, which is respect to the actual solver we're using. And the MiniZinc compiler will push that into some FlatZinc, which is a low-level language, which is read directly by the solver. The solver reads that and spits out a solution. So we have this kind of separation of compilation from solving, because that turns out to be very useful, because solvers are the kind of trying to do a very different thing than the compilation process. So one of the key things about MiniZinc was it's designed to be solver independent, so we can use any kind of solver at the back end. So we can use constraint programming solvers, which were originally designed for, but also mixed integer programming solvers, which is probably the most used discrete optimization technology, Boolean satisfiability solvers, or SAT modular theory solvers, or constraint-based local search solvers, for example. And it turns out that lots of people need to solve discrete optimization problems, so there's a lot of use of MiniZinc around the world, and nicely, some of it far from the constraint programming field. I read papers which refer and use MiniZinc, but they don't actually really know that much about constraint programming. They're just using it as a tool to solve their problem. So MiniZinc is kind of a victim of its own success, because it was designed for constraint programming problems, right? So in constraint programming problems, you have a small number of highly complex global constraints. So a great example in my mind is this rotating workforce scheduling problem. So this is where I have to build a schedule where everyone runs the same schedule, so a rotating one. And it actually turns out to be two constraints, two global constraints. The constraints are very complicated, and to set them up takes a little bit of work, but this is actually used to solve commercial workforce scheduling problems. So just two constraints, very complicated ones. So that was sort of where CP models were designed for. And if you look at the job shop scheduling problem I talked about, so if you have even 10 tasks and 10 jobs with 10 tasks each, that's only 100 variables and about 100 more constraints. So we're used to solving these things with a small number of highly complex constraints. But it turns out MiniZinc is used for MIP and SAT models, where we typically generate maybe hundreds of thousands of simple constraints. Okay, so a bit of difference in the kind of the implicit assumptions that went into the language. Also, MiniZinc was designed to solve NP-hard problems. Okay, so here the solve time is large even for small models. So the job shop scheduling examples, there's some famous examples which are 10 by 10, so 10 jobs with 10 machines, so only really 100 decisions to make, which were still, we didn't know the optimal answer 30 years after they were initially posed. Right? So these are difficult, challenging problems that we're trying to solve. But it turns out people out there use MiniZinc to solve very easy problems. So in these problems, the solve time is effectively instantaneous, even for large models. So for example, our mortgage program there, we can run mortgages for 10,000 time periods if you want to go paying mortgage on every day, and we can solve that very easily. Okay, so all of that you can see is that because the assumptions in MiniZinc when we're building it, where we're going to sort of create a model with a few hundred constraints, doesn't turn out to be correct. And what happens is the translation time ends up being too slow. It starts to dominate the process because we have thought, well, the solving is going to be NP hard, the problem is going to be NP hard, so the solving is always going to dominate the translation time. And another thing is that, as I mentioned earlier, many discrete optimization problems actually aren't solved by just solving a single problem. What we end up doing is repeatedly solving a very similar problem. So we have this kind of incremental usage of discrete optimization. So a simple example is lexicographic minimization. Let's say I want to minimize this XYZ triple. A simple way to implement that using an existing solver, which doesn't support lexicographic minimization typically, is that I'll find a solution to the problem, let's call it A, B, and C, and then I'll add a constraint. Well, if the new solution, XYZ, has to be less than A, B, C, right? That's a lexicographic constraint that I can add to my system. And then I repeat the process. Now I find a new solution that has to be better because I added this lex constraint, and I'll keep going around until I find no solution, then the last constraint I found is optimal. So you can see that I'm solving almost the same problem, but adding one constraint every time. And probably much more importantly in practice is what's called large neighborhood search. So this is a very powerful technique used to solve many real-world problems to get very good solutions for them. So we find a solution, doesn't matter how good it is, we fix most of the parts of the solution. So we actually end up with a very much smaller problem because basically we're fixing most of the existing constraints and variables. And then we search for a better solution just in the parts that we haven't fixed. And then we do that again and again and again. And we change where we're looking, change where we fix, and we can find better and better solutions. So this is a very powerful sort of meta-heuristic approach. And again, you can see that it's highly incremental. We sort of solve the problem. We then go around, fix most of the variables in the problem, and then solve again. So it turns out that MiniZinc is often used in this sort of framework, where essentially we've got our compiler builds a model, sends it to the solver, gets a solution, and then the incremental meta-heuristic search sort of says, oh, we have to adjust our model, and then we're going to recompile it and then go around and loop this again. Okay, and you can see that the problem with this sort of picture is that we recompile the entire model on every small change. So we're not making use of the fact that most of the problem that we started off with hasn't changed. The search heuristic has added some constraints or changed some constraints a little bit, but most things have stayed the same. And so we end up doing a lot of time in this compilation process because we keep doing it every time around the loop. So what's the answer? Well, the answer is MiniZinc 3.0. And so let me talk to you a bit about that. So in Zinc, we tried compilation completely. So compiling the model compiled completely and then would run on the program data. That turned out to be very, very challenging. So MiniZinc doesn't work that way. MiniZinc is just an interpreter, essentially. It rewrites system that relies on the problem data. And what MiniZinc 3 is an efficient incremental rewriting language. So we sort of added some steps into the picture. So now MiniZinc compiles to MicroZinc. So that's basically just compiling down to a small subset of MiniZinc to get rid of some of the complexities. But that's independent of the data. And then MicroZinc is rewritten to NanoZinc, which is essentially FlatZinc, but a list of variables and defining constraints. And one of the important things about NanoZinc is it's going to keep track of variables and defining constraints in more detail than just a flat thing. So FlatZinc is what a solver wants. So basically solvers can only answer questions, existentially quantified questions. So they basically want a list of variables, the decision variables, and a list of constraints, nothing else. That's what they deal with. We can't change what they can deal with. So the new architecture of MiniZinc looks like this. We take our model, we compile that to a bytecode, and then that bytecode is what's interpreted with the data. And obviously you can see that we're going to reduce our compilation time there, and hopefully we can make the interpreter fast. We have sped up things a lot. And then of course that spits out solver-dependent NanoZinc, which is quickly translated to FlatZinc. The solver runs it. The search heuristic sits inside here and either decides that we found a solution or updates the model in an incremental way, and we run around this loop. And the idea is that we can run around this loop a lot faster because we're not redoing a whole lot of work. So the MicroZinc interpreter is incremental, meaning every small change is the only part of the work that we have to do. So just to give you an idea about what that looks like and the sort of punchline, which I'll get to near the end, let's have a look at MiniZinc 3.0 in a bit more detail. So MicroZinc is basically a minimal subset of MiniZinc. Contains pure and total functions, and this is important in general. MiniZinc is filled with partial functions because once you start doing things with arrays, partial functions occur all the time because we get array out of bounds errors. We compile those things away. Let expressions are the critical thing. This is how we introduce constraints into a problem. And if then else expressions here where they're decidable at the interpretation time. So once we have the data, we know which branch we're going to take. So when these are not things that are going to the compiler to decide. And array comprehensions. And that's basically all of that's actually in MicroZinc. And the interesting thing is NanoZinc, which is very similar to FlatZinc, right? So we have variable declarations, but we've attached constraints to them. So we're keeping track of what are the constraints which help define this variable, right? And each of those defining constraints has to be flat, basically, so each sub-expression is named. So those could be built-ins like int minus, or MicroZinc predicates like ABS, or absolute value of u is v. Okay, so essentially we have this challenge for any kind of declarative language that we want to write down functional expressions because that's a natural way to write down constraints. But in the end, we're going to talk to a solver which only understands relational things. So solvers just take a list of variables and a list of constraints and nothing else. But one thing that we understood more and more about MiniZinc after we got to this level of 3.0 is that most of what the MiniZinc interpreter is doing is really some kind of constraint propagation. So we're starting from an initial high-level model, we're mapping it to a low-level model. A lot of what we're doing here is simplifying expressions. We're tightening bounds on variables. So if we know that variables can't take specific values, we're going to shrink those, remove those, and that'll actually help us make the model smaller. We need to eliminate redundant constraints. So we'll generate lots of constraints, and then some of them will turn out to be useless or not relevant to the problem. And we need to eliminate dead variables, so constraints that don't really say anything more because we sort of introduced the variables that then we got rid of them. And I'll show you examples of this in a moment. And more importantly, you also need to substitute one variable for another. So we're going to build up aliasing during the translation of the model. We want to make use of that. And common sub-expression elimination is critical in these problems because if you're solving an optimization problem, or a discrete optimization problem, you don't want to have two copies which are really the same variable. So if they end up being the same variable, you sort of artificially increase your search space by at least a factor of 2. So all these things are crucial for solving performance later on. So just to give you an idea about how a kind of MiniZinc interpretation compilation process happens, here's a kind of simple example. I've basically got one constraint that's reasonably complicated. It's x times y div z plus y plus 1 running equal to absolute value y minus z. And I've got my 3 variables here with their initial domains from minus 10 to 10 for x, 0 to 10 for y, minus 10 to minus 1 for z. So here is the NanoZinc that would be created. Essentially, you can see we're basically building up names for each of the sub-expressions which occur in this complex constraint. So u is y minus z, and we've actually done a bit of reasoning to say, well, the values that you could take are between 1 and 20, the initial domain of u between 1 and 20. And then v is the absolute value of u, etc. We work that out. W is the result of the y div z. And notice here, and this is part of what it takes to handle division correctly. So in this constraint system here, we not only know that W is Y div Z, but we also know that Z can't be 0, right? So in a declarative system, then division by 0 basically is false. You can't divide by 0, so we know that because this thing is there does not equal 0. So we've got to be a bit careful of that, but we'll treat it in the simpler way here, just for simplicity. And then finally, we have one constraint at the top. In fact, we have a Boolean variable at the top, which gathers all the sort of global constraints of the model, which is the linear constraint that we're talking about with all the components in there. And actually, it's very easy to translate that to FlatZinc. Basically, every line becomes a line in FlatZinc where we've basically changed the constraints into the FlatZinc form, which is always sort of predicate the variable calls. The only complicated one there is the linear constraint at the end. Okay, so there's our model, our starting model. What does our interpreter want to do? Well, our interpreter wants to make sure that it does all the reasoning it can about this model to make it as simple as possible, so the constraint solver doesn't have to do things. So for example, we can look at u. Well, use a positive variable, takes values from 1 to 20. So actually the absolute value of u is u, right? So we can just do that substitution. So once we've done that, well, we can substitute for v, the value of u, right? If v is u, we can just substitute away. And then because u is actually a linear expression and this is a linear constraint, well, we can substitute for u in this linear expression. We'll still get another linear expression. So that's still a constraint, a single constraint that our solvers can handle, complicated linear constraints. And we can do some simplification. So, right, I want to get to there. Okay, you can see that we can subtract y from both sides, simplify it out. And I can also finally say, well, z not equal to 0 is true because z can only take values which are negative, so it can't be 0. So basically then I can remove these variables u and v because they don't do anything. Obviously I can remove the constraint too, it's also doing nothing. So I don't refer to u and v anymore, and therefore they can be removed completely. Okay, so basically this is the process of sort of constraint propagation that's happening inside things. So I'm avoiding, well, of course, a lot of the other parts is unrolling loops. So basically we have list comprehensions and we have to unroll them. That's the other major thing that goes on, but I won't show that in an example. Okay, since u is not referred to in any of the defining constraints outside its defining constraints. So obviously we still had this constraint u equals y minus z, but since no one referred to u outside, that was irrelevant. Okay, so if we did our interpretation, we got this model, we might have run it off, and then LNS came back and said, well, I need you to rerun the model, but now I'm going to fix x to 0. Or it could be in the rest of the compilation, we've discovered some other system constraints which forced x to be 0. So we want to keep going, right? So basically we need our compilation to be incremental. As we're getting more and more information, we're incrementally improving our model. So obviously if x is 0, we can substitute out its domain, it should be 0. And then we can substitute for x where it appears, right? We get 0 times w. We can obviously simplify that expression. Now we know that t is 0. We can just change its domain, so it's 0. And then we can substitute for it where it occurs. Then I can look at this constraint on z. I can say, well, actually that says that z is greater than or equal to -1. So I can update the bounds on z. Okay, so actually now z is fixed as well. And essentially then I don't care about anything else. And so all the other constraints become dead. And I end up with basically just this set of variables and no constraints. Obviously in practice, there'd be other constraints in part of the model. So hopefully you can see why we need to keep track of the constraints that define a variable is that variables become unreferenced and then we want to get rid of those constraints. And in particular, this is really important for the example that I show at the end. So basically, often I'll do something like this. It looks silly, but it'll happen. Is I'll build some large array of variables for some large complex expression, and then I'll just use one copy of it. So I'll look up the first element in the array and use that for something. And if we're not careful, what happens is I'll build this, well, what we'll be able to do now is in the best case, we'll build up this huge number of expressions, many, many copies, but then finally we only refer to one and we'll be able to throw away all the rest. what we want to get to eventually, of course, is to be able to hoist essentially this behavior, realize that we're only going to make one copy of this one copy of this array in the end, and not have to build up the huge number of copies. Of course, the problem is that when this index value 1 at the end, so I'm looking at this big array only in the first element, if this is unknown, if it's a variable when I'm building the array, of course, I don't know that it's only going to be 1. So there's the challenges in designing MiniZinc 3.0 are efficient reference counting, but essentially the references in the defining constraints do not count to that variable. And this has to work with aliasing and common substitution elimination. So it's clearly the case that we can build a constraint for absolute value of x, a constraint that defines absolute value of y, and then later on find that x equals y. And in particular, if we've got large numbers of expressions, we want to be able to handle this as efficiently as possible. So it's by no means a solved problem, but I want to sort of express that there's interesting challenges in building this sort of view. So one of the things that is very, yep.
2 minutes?
2 minutes, okay. Oh, yeah, I should have been careful. All right, so I just want to talk about incrementality. So,
okay, there's still a panel coming later.
Yeah, okay, good. Yeah, I was running, the thing ran short when I first gave this talk, so obviously with my, I've got more expressive. I just talk about incrementality. So we can add a predicate in. If it has no definition, then it'll just do nothing. So into the flat thing. So our MiniZinc can have a definition for lex min 0 with nothing and a whole lot of other constraints, and nothing will go to the solver. But then if this predicate is defined in the next time around, it can be defined as above. So it'll give the previous solution and add a new lex constraint. So this is exactly implementing the lex optimization that I talked about. And so the nice thing here is this predicate is sort of a placeholder for constraints we're going to add in the future. In fact, we don't need to do that because we only need the last lex less constraint. We can just have a simpler constraint, which just adds this lex less constraint. But then we need to undo the previous one, right? We only need the last one. So we want to actually backtrack to where we were, the original base model, and then add a lex less constraint for the previous, just the previous solution, nothing before that. And so that means our MiniZinc 3.0 has to support backtracking. So we have to have this, be able to go back to a previous state of the solver or compiler, in fact. And we also have this notion of like continuations, if you want, which are currently undefined, which will add more constraints in the future. So the interesting thing is what we've kind of done is we've recreated a CLP system, and I'll come back to that more in the conclusion slide. So it works. You can see that it takes less time to do model compilation and usually uses less space. More importantly, if you use it for something incremental, you get a massive reduction in compilation time, right? Because you're only compiling the incremental part. And actually that can often help in solving time as well. And sort of the conclusion is, so CP modeling language lost a lot of the expressiveness of CLP. But if you look at what we've done with MiniZinc 3.0, we've in some sense recreated a CLP solver. So our incremental compiler is a propagation solver. So essentially the way we think about compiling MiniZinc is actually applying propagation. So it's as if our CLP system is sort of taking the model and rewriting it completely. That's a kind of solving, a propagation solving. We had continuations for incrementality, and those are absolutely analogous to CLP predicates. A continuation is essentially a placeholder for where we're going to add some more constraints in the future. And backtracking has to be supported because often when we're using incremental systems, we want to be able to backtrack to like the base level model and then add new constraints and then backtrack again to the base level model and add constraints. So we've added in all the features we sort of got rid of when we moved from CLP to CP modeling, or CP modeling languages. From our perspective, of course, the most important thing is more efficient compile time, and particularly for the incremental use. And it can produce more efficient flat sync because we track the dependency between variables live. So as we do incremental compilation, we can get rid of stuff which sits seemed to be useful when it was created, but became dead. And that happens more often than you believe in discrete optimization models. And the other big advantage, which we haven't demonstrated here, is that incremental solvers can take advantage of that incrementality. And so I guess one of the lessons, I guess everyone from a programming language perspective understands this, is once in a while you basically have to rebuild your system from scratch. So building MiniZinc 3.0, we're by no means got to a point where we can release it, but by thinking about it from first principles again and understanding what we are missing, what it couldn't do well, we can rebuild a system which we hope is much better. And for me, the most interesting thing was this old good idea. So many of the ideas of CLP have basically been recreated in this new version of MiniZinc. And hopefully that I found that very interesting. So questions?
Very nice. Well, let's thank Peter. Virtual applause. I think we'll leave